Efficomp Air and Energy Consulting Services presents energy savings in compressed air systems. A warm welcome to all who are connected with us. The thought behind this channel is for imparting knowledge to the people on compressed air system, as in compressed air system is one of the most neglected but one of the critical utilities in many plants. These training sessions will help you to find easy methods for savings and also to gain technical expertise on individual components of the compressed air systems. The channel will be maintained by the owner of the company, Mr. Dhirendra Shukla, who will guide and deliver lectures. As said, Mr. Dhirendra Shukla has more than 20 years of experience in this field. He has worked with many compressor manufacturers and also been part of product R&D. He is an active presenter with many government organizations with more than 200 plus audit experience.
Hello friends, it's a pleasure to introduce myself through this learning channel. It gives me a good platform to share my knowledge with customers, engineers and people in the field of utility management. I have been working in this field from past 20 years and energy saving in compressed air system excites me. I'll be posting a series of videos to showcase saving opportunities, working philosophies of individual component and its importance. We are a professional energy audit company and are actively in the field of energy management and savings for our customer. You may contact us for any such audit requirements. For any queries regarding these training sessions, you may comment or contact us, but for that, you need to subscribe our channel. I can assure you of great knowledge gain through these videos, which will surely help you. So let's begin with the introductory session. Compressed air is the second most critical utility after electricity for any plant. Mostly all industries use air compressor for instrumentation and other purposes. The operating cost in any industry for compressed air is generally around 10% of the overall power bill. But for few industries highlighted here in the slide, it can be as high as 30% of the operating cost. Few major compressed air consuming industries are automobiles, cement, steel, textile, tire, pharma, etc. Whenever we talk about any utility like steam, electricity or water, we focus on operating efficiencies and life cycle cost. Whereas I have seen that the same is not followed for compressed air. People focus on the initial investment cost only on the compressed air system, whereas they don't focus on the life cycle cost of the system, which is around 10 years. Looking at the graph, you can easily see that the life cycle cost of a compressed air system mainly comprises of the energy cost, which is around 80%. Capital investment costs are around only 4%. So our focus must be on the 80% portion rather than on the 4% investment cost during equipment selection for compressed air system. Compared to other utilities like steam, electricity, water, which has their operating efficiencies more than 60%, compressors have the operating efficiencies only in the range of 15% of the total input. So the diagrammatical representation clearly depicts that 8 horsepower of electrical input yields only 1 horsepower of compressed air power and the rest is lost as heat. Hence, whenever we are wasting any compressed air, say through leaks, misuse, we must be aware that compressed air is the costliest utility of any plant. Yes, you heard it right. It is the costliest utility of any plant. So moving ahead, whenever we talk about compressed air system, our focus generally goes to the air compressors rather than looking at it as a system. For any system, the supply is only when there is a demand. So any impact or saving in the demand side or in the distribution side has a direct impact on the supply side operation and results in good savings. Hence, rather than focusing on the supply side, it is advised to look at it as a system, and individual component of the system must be given due importance to achieve savings and operational efficiencies. Before we start with the saving opportunity discussion, just a small intro on types of compressors. Compressors are mainly divided in two groups: positive displacement and dynamic type. Positive displacement work on the principle of volume reduction, that is, pressure increases with reduction in volume, whereas dynamic compressor works on the criteria of kinetic energy conversion to pressure energy. In industry, you will generally see two types of positive displacement compressors, one of them being reciprocating type and the second screw type. They both work on the criteria of volume reduction, wherein a specified volume of atmospheric air is compressed to the desired pressure with reduction in the volume of the air. In reciprocating compressor, it is achieved through a cylinder and piston arrangement, whereas for screw compressors, the same action is done through two numbers opposite moving screw elements, where atmospheric air gets trapped in between the screw elements and gradually the area goes on decreasing, which results in volume reduction and in turn increase in the pressure. All positive displacement type compressors are also termed as constant volume machines, as their volume delivered remains same irrespective of the delivery pressure. Volume delivery of positive displacement compressors can be altered with reduction in the prime mover speed, that is the electrical motor, and hence it should be noted that RPM also plays an important role in the compressor volume delivered. Herein in the slide you can see the reciprocating type on the upper picture and the screw compressor on the lower picture. When we talk about dynamic type compressors, you will generally see centrifugal compressors used in industries. They are used for large demand requirements, and they are generally termed as base load machines. Centrifugal compressors work on the criteria of giving kinetic energy to the atmospheric air and then converting that kinetic energy to pressure energy by sudden obstruction to the high velocity air coming out from the impeller with help of a diffuser. Centrifugal compressors are also termed as constant pressure machines, and they operate according to their operating curve ranges defined. So whenever we talk about energy savings in compressor system, our approach should be a reverse. That means starting from the demand distribution and then coming to the supply end. So whenever we talk about demand side of a compressor system, the easiest and one of the biggest loss in the system we find are the leakages. Leakages can be through pipe joints, drains, hose pipe and fittings, FRLs, etc. Demand side comprises of all the users consuming compressed air, and it has direct impact on the supply. That means the compressor operation. When we look at general industry demand pattern, we see that out of the total productive demand, around 20% is lost in air leaks only. And this demand of leakage is part of the plant demand, and the compressors work to fulfill the leaks also. So after the demand for leaks, the other available air is available for the productive demand. With leaks forming the biggest loss in the system, it also presents with the easiest way to save energy. To quantify the amount of leak loss in any plant, there is one simple method using which an estimation on the leak loss can be found easily. So as shown in the slide, during holiday in the plant, we can do this exercise. Once the complete plant is stopped, shut off compressed air operated equipments, run compressors to fill air in the system. No user should be consuming air during this trial. Once the system fills with compressed air and loading unloading of the compressor starts, note down the load and unload timing using a stopwatch. Use the formula shown in the slide to calculate the leak loss. Take at least 5 readings of the loading unloading cycle and make an average value for the loading and unloading time values before putting in the formula. Once calculated, the formula will give you approximate percentage loss in the plant due to air leakages. You can multiply the compressor capacity, that is the CFM of the working compressor which you started during this trial, to get an approximate CFM loss through the leaks. Leak finding is an continual improvement activity of any plant, and a quarterly inspection must be done to achieve good savings through reduction in leak losses. In this slide, some standard minimum, maximum and average readings observed during audits in different industries is shown. So leakages can be as high as 50% of the total supplied quantity. Hence, they must be prevented or reduced periodically. So if you see, if the operating cost, for example, of a compressed air system is 1 crore for a year and 20% is leakages, so you can calculate that easily 20 lakhs can be saved in a year if the leakages are attacked. Moving to the distribution system, it mainly comprises of the headers and the drops. Headers are main component of the distribution system, and they are generally of two types: the ring main system and dead end type system. An improperly designed header may lead to pressure loss in the user section, and for compensation of the same, compressors have to work on higher pressure. There is a direct correlation between compressor pressure increase on power, which is around 7% for every 1 bar increase or decrease in the pressure. So, distribution system must be designed taking in account the overall pressure drop, which should not be more than 7 psi for any system once the compressed air is supplied to the plant. In a dead end system, there is only one single line running from point of origin, that is the compressor house, to the user section. A diagrammatical representation of the same is shown here in the slide. If a user number 5 needs any air, he has to wait for air to come all the way after all other users like user 1 to 4 have consumed air. In this scenario, generally user 5 is always starving for compressed air and pressure drop is a common problem. To overcome this, generally the compressor operating pressure are raised and it further increases the power consumption of the system. And hence generally dead end systems are not recommended for compressed air systems. So to overcome issues in dead end type piping system, a ring main system is proposed. In a ring main system, the main supply header is connected back to the same supply header, creating a loop. This creates two passages for the compressed air to flow in the pipe, as you see in the diagram. So if we consider earlier scenario of dead end system, now user 5 can get air from both sides of the piping rather than depending only on the earlier circuit for air requirement. A ring or loop system also reduces velocity of air in the pipeline, further reducing pressure drops, and thus can help reduce supply pressure in the compressor house, leading to energy saving on the power consumptions. Now moving to the supply side of a compressed air system, which comprises of the compressor, filter, dryer, demand controllers and air receivers. In supply side, air receiver is one of the key components, which helps to reduce sudden air supply jerks and stores sufficient compressed air in the system to reduce cycling of the compressors. For every plant, there has to be a minimum storage size to counter sudden demand and sudden compressor stoppages. The term used to define the effective storage is called as capacitance. A receiver acts like an electrical capacitor bank. It stores when the supply is excess and releases when the demand is more. Capacitance is termed as the amount of compressed air needed to be supplied or removed from the system to raise or reduce the system pressure by 1 psi. Higher the capacitance, lower will be the rate of pressure drop over time, and the unit is denoted is with feet cube per psi. It should be noted that for compressed air system, there is a terminology called as big is beautiful in terms of piping and air receivers. So higher the size of pipe, or higher the size of receiver, it is always going to help the system. A formula for system capacitance calculation is shown in the slide. You can use it to define the minimum storage capacity which can support production during sudden demands or say any compressor stoppage for a certain period of time. If properly designed, the compressor operating time can also be reduced, leading to saving in compressor power consumption. Air dryers also form an important part of an compressed air supply side. They are generally of two main types used in an industry, refrigerator type and desiccant type. As we move from refrigerant to the desiccant type of dryers, the quality of water removal increases. That is, the air quality improves. But air quality has its own cost. Higher the quality, higher is the cost involved with it. Dryer selection must be done purely on the user's requirement. A refrigerated dryer is which works on the criteria of a refrigeration cycle, wherein compressed air is cooled in an refrigerant to air heat exchanger up to 3 degrees centigrade in pressurized condition, at which due to the cooling effect, water in the compressed air condenses. For normal plant air system, refrigerant dryers are good enough to remove moisture and can fairly support or supply good quality of air. They have very less pressure drop across the heat exchanger compared to other type of dryers, due to which the generation pressure needs to be raised, which leads to further increased power consumption by the compressors. Moving to the desiccant type dryer, they are mainly of four types, which are heatless, externally heated type, externally heated with blower, and heat of compression type. The quality of air coming out from a desiccant dryer is of higher dew point, generally minus 40 degrees C ADP, but the operating cost for this type of dryer is very high. A desiccant dryer works on the principle of adsorption, where compressed air passes through a tower filled with alumina or silica gel, which has great affinity towards moisture, and it absorbs moisture from compressed air. But once the tower fills with moisture completely, that is when it gets saturated, it again requires to be regenerated back to original condition. During this time, compressed air passes through second tower of the dryer, but around 12% of the outgoing treated air is again thrown back through the first saturated tower to remove the moisture for regeneration. Around 12% use of compressed air is really high for any compressed air system, and it is equal to addition of 12% demand on the compressor itself. Hence, desiccant dryers should only be used when higher quality of air is required. Otherwise, a refrigerant type dryer suffices to most user requirements. A representation of the process of the adsorption is shown here. This particular slide shows the process of regeneration of a saturated tower from which moisture needs to be removed for getting it ready for further use of drying. The air used for regeneration comes from the same system outgoing compressed air. This slide shows the compressed air flow circuit in a desiccant dryer, which shows the drying cycle as well as the regeneration cycle also. The purge losses in a simple heatless dryer can be as high as 12%. Further, the pressure drop across these kind of dryers are higher, around say 5 to 7 psi, which further requires to be compensated by increasing the compressor operating pressure. Hence, two main points, that is the purge loss of 12% and the pressure drop created, must be taken in account before selecting this type of dryer for a system. It directly adds to the operating cost. Going ahead, as we discussed during the initial opening slides, around 80% of the power given to an air compressor is lost in heat. which can be easily recovered from the compressor for space heating, water heating for processes, boiler makeup water heating, etc. An air compressor can heat water up to 80 degrees centigrade, which can be utilized for many industrial processes. Around 60 to 70% of the motor power equivalent heat can be extracted from an air compressor, which can lead to fuel cost saving. One of the other saving areas is the supply pressure optimization. A demand controller is a device which is installed just after an air receiver to create a positive buffer. It does not allow any excess pressure to go to plant users, which in turn helps to reduce plant artificial demand and also leak quantity. It has a functionality similar to a water dam, which releases as per demand and stops any free uncontrolled flow to the plant users. If sized properly with correct system output pressure defined, a demand controller can lead to savings in compressor operating power from 6 to 20%. Some sample graph of a system with demand controller are shown in the slide, which shows the impact of controlled release of the system air pressure. Traps are also very important and key part of saving in compressed air system. They help to remove condensed moisture from the system. If not installed, people generally tend to keep open the drain valves manually, which leads to loss of costly compressed air. The most suitable type of trap is a zero loss drain trap, which helps to remove only moisture from the system without wasting any compressed air. In compressed air system, there are virtually 4 to 5 traps which needs to be installed at compressor, aftercooler, air dryer, air receiver and plant header lines. They are mechanical and electronically operated type. The slide summarizes the points we discussed for easy energy savings in compressed air system: reducing leaks, stabilizing system pressure, eliminating misuse, properly sizing the receivers, reducing pressure drop across dryer, piping must be incorporated in the system operating. The overall discussion here clearly indicates that compressed air system is dynamic in nature and must be managed from supply to demand side. It requires complete system audit to pinpoint areas for improvement in the system, which may be in the demand side, distribution side or supply side. It must be managed as a system rather than just focusing on the generation side. A complete improvement cycle is shown herein to sustain the system reliability and efficiency. Also to note that this is an introductory session on simple and easiest saving opportunities in compressed air system. Going ahead in future videos, we will be discussing on individual system components, details and their impact in the operation and costs. So friends, this was our introductory session. The topics covered here are basic, but the people in this field know that it's a big ocean. So in the next upcoming videos, we'll be covering each component in brief. Stay connected. Thank you.
Hope you liked our introductory session. For more such informative and educative training sessions, do subscribe and watch our future videos. For any queries, you can contact or email us on efficompair@gmail.com. Thank you.